Hi, I'm going to be talking about building an optical character recognition agent using neural nets. The first slide is the abstract, which defines the general overview of the paper and of the project. The learning algorithm in this project is based on the artificial neural nets, ANN. The input of this algorithm is a data set acquired from UCI machine learning repo, and the output includes statistics on the learning outcomes, such as the validation set accuracy and the mean squared error. Overall, this project has been an exercise into exploring the different relationships between what goes in as input to the neural net, for example, the learning rate or the momentum, and what comes out, which is, for example, the validation set accuracy or the general set accuracy. And really, it's an exploration in the relationships between the inputs and the outputs. The overall goals for this project, as I mentioned in the last slide, was obviously number one, to explore that relationship between the various aspects of the learning algorithm. Another thing that I explored was changing the number of input nodes, keeping the number of hidden nodes constant, and changing the number of hidden nodes, keeping the number of input nodes constant in the neural network to produce an output and see and plot the validation's mean square error and see the trends in that, and to be able to find an optimal structure for the neural net if that exists, given that in the academic community, or in the academic research rather, there isn't a lot of clarity on what an optimal neural network structure is, and if there's an optimal neural network structure at all to begin with. The next slide is explaining what a neural net is. The basics of the neural net is that there's an input layer towards the left hand side, which is in green, the hidden layer is in purple, and the output layer is in red. As you can see, every input and hidden layer, every hidden layer really represents every hidden layer node represents one perceptron. And the idea of neural net is to take the perceptron, which is only a linear classifier, and make that into a non-linear classifier by combining the different perceptrons. The three types of parameters typically that define an ANN are: number one, the interconnection pattern between the different layers of neurons; number two is the learning process for updating the weights of the interconnections; and number three is the activation function that converts a neuron's weighted input to its output activation. Another thing worth mentioning here is the backpropagation learning algorithm, which is what this neural net in my algorithm is based on. And that can be divided into two phases: the propagation and the weight update. Details on that are in the paper, and I will not go into that right now during this presentation. The next slide is a description of the learning outcome metrics. So as I talked about earlier, we're going to be exploring the validation set accuracy and the general set accuracy and various other metrics. So these are kind of a list of those metrics and an explanation for each one. Obviously, the training set accuracy is the number of correctly classified patterns over the total number of patterns in the training set. The generalized set accuracy is the number of correctly classified patterns over the total number of patterns in the generalized set for an epoch. This represents the accuracy of the network in dealing with unseen patterns. So yeah, generalization set accuracy is how your algorithm can deal with unseen patterns and how it can generalize beyond the data that it already has. There is more information in the project report again, and these outcomes, this list does not include the validation set accuracy and mean squared error, but that has a similar idea as the ones mentioned here. Now a little bit into the code. The directory structure of the code looks like this. There are four, as you can see, main files, in the sense main.cpp, dataentry.h, datareader.h, and neuralnetwork.h. The Excel files, which are letter A recognition, letter recognition.csv, are CSV files, actually, which have the data from the UCI machine learning repository, slightly modified to fit the input of our algorithm, and the results are stored in results.csv. Some more information about how and I'm going to be giving a live demo later at the end of this video, but this is what this looks like. There's a sample output screen and a main.cpp. The sample output screen has a kind of text designed output which is more comfortable and readable for the user as opposed to just throwing them information. And main.cpp shows the various parameters that can be set. As you can see, then there's a neural network NN, which sets the number of hidden nodes, input nodes, and output neurons. It sets, there's a learning momentum and learning rate set, and then there's this desired accuracy. Some more detail about the code is that main.cpp is responsible for initializing the setting and setting up the neural network, pointing the algorithm to the right data and result files. Data entry.h is the header file defining double pattern, double target, which are to store the pattern and target data respectively. Data reader.h is responsible for populating the pattern and target fields. It loads the data set as the input and processes each line, decoding the raw information and converting to the pattern target model of deciphered data to be used by the neural network. Lastly, the neural network.h file is responsible for implementing the neural network structure and basically deals with the backpropagation network and also calculates the various metrics that we talked about, which define the learning outcome. Now, these are the more interesting slides about the results. The first result is momentum versus accuracy. As you can see, the figures show the effect of having the momentum value set to a high level. The second one is 0.8, and the first one is no momentum. Clearly, the convergence is fast in the case of momentum. Additionally, what happens is when you have the momentum, it enables the backpropagation algorithm to avoid any local minimas in the search space and to explore areas where the error space may not change. So this is a pretty interesting result. The second is learning rate versus the number of epochs required to learn desired accuracy. This is somewhat expected. As you increase the learning rate, the number of epochs required to reach a certain level of desired accuracy, which in this example is 95%, is decreased as you increase the learning rate, which is very understandable. So from 0.0009 or 4 zeros and 9 has a much higher number of epochs required as opposed to when you go to 0.005 or 0.005, 3 zeros and 5, which drops the number of epochs required to 5. So that's definitely something that is expected. The next result is validation MSE versus number of nodes. So these two figures show the validation MSE and changing the number of nodes. So in the first figure towards the left, we did not change the number of input nodes, but we changed the number of hidden nodes. So we changed the number of hidden nodes from 2, 5, 10, 20, and 50, and we kept the number of input nodes constant at 10. And as you can see, I applied this function on the validation MSE to kind of magnify the results and show it more clearly, but as you can see, the fluctuation is pretty clear. This also shows that there is perhaps not an optimal solution to many problems because as far as the number of hidden nodes go, because it's very specific to the particular problem. So you just have to try it out. So in our case, luckily, like as you increase the number of hidden nodes, the validation MSE at some point decreases to a very low level. But of course, there's all of this fluctuation, which is kind of unpredictable. And then there is, on the right hand side, we kept the number of input nodes variable and number of hidden nodes constant at 10. So as you can see, from 2 to 5, when we increase the number of input nodes, there is a remarkable improvement, or there's a remarkable increase, I guess, in the validation set MSE, which is not exactly a good thing. But then it kind of plateaus out, which kind of shows that beyond a point when you increase the number of input nodes, it doesn't really affect the learning outcome as much as you would think. And so that's all the slides, and these are the sources. Thank you for listening, and I will be now taking you to the live demo, which I'm going to just figure out. So this is, as you can see, this is the input which I just put in. As you can see, the learning parameter for learning rate is 0.001, and the momentum is 0.8. The desired accuracy is 99. And and this is a letter A recognition.csv, which means that this will learn how to recognize a letter A from all the other letters. So it's a relatively simple learning problem. The neural network structure is 2, 10, and 1, which is 2 input nodes, 10 hidden nodes, and 1 output node. So I'm going to be showing the output to this. Let me just run it for you. And okay, so this is what we got. So as you can see, this is kind of our output. So this prints all the epochs. So we go from like a relatively low kind of learning rate on training set accuracy, and as we increase the number of epochs, it kind of increases from 6, 7, 9, and eventually it comes and plateaus at 95.8 and then to 95.9. And this is what kind of our 26th or 25th epo looks like, as you can see. This is where it kind of plateaus out, and then the rest is kind of just, we could have quit, but in the code I just made it not quit, and just to show the final results. And then I'm just gonna try to fit this in. These are the statistics at the end, which is 50 elapsed epochs, which is what we specified. The validation set accuracy is 96.2 in the end. The MSE is 0.0367352, and the journal set accuracy is 96.375%. So this is kind of like a demo of like how this works, and obviously you can kind of mess with this inputs here to kind of see if you can come up with better results. But yeah, mostly given the simplicity of the data set that I've been using, the variations definitely doesn't exist to that extent. But this will definitely be more seeable when we go and apply this to a real world kind of situation where you're, say, doing handwriting recognition. So yeah, that's it. Thank you.